of this session. It's my pleasure to introduce Helena REICHLOVA from TU Dresden, and she will tell us about imaging, non-collinear angular analysis using thermal-grade microscopy.
Yeah. So thank you for the introduction. Thank you for the opportunity to present our results. As Akash said, I'm from the Technical University of Dresden, but this work was done together with a lot of people, mainly from Prague and other Dresden groups. And recently we have also a very nice collaboration with the Bielefeld University. And it will be imaging technique, another imaging technique, and this time we try to look at the non-collinear antiferromagnets. So collinear, non-collinear, this was discussed here many times, both of them. And as Matthias, for example, mentioned yesterday, the collinear antiferromagnets are amazing. They show so many cool effects. And it's so cool to imagine that the arrows are really like pointing in some direction, and under some current pulse or under some field, they are flipping, they are doing something. On the other hand, the non-collinear antiferromagnets, even the ground state, even the orientation of the arrows, of the spins, is not clear, or it's, let's say, discussed. And then, of course, when one thinks what they are doing under magnetic field, under electric currents or whatever, it's much more complex. But maybe partly due to this complexity, they are also luckily showing a lot of important spintronic phenomena which were not observed, or which are, let's say, a little bit more complicated in the collinear antiferromagnets. For example, anomalous Hall effect, anomalous Nernst effect, and even such an important phenomena like a spin transfer torque, which is, let's say, predicted to be weak in the collinear antiferromagnets, are predicted to be present in the non-collinear antiferromagnets. So there is certainly a motivation to understand these beasts a little bit better. And then when one dreams about, let's say, observing spin transfer torque or domain wall motion or whatever, what one like experimentally starts, or what one wants to do experimentally, one wants to have probably some thin epitaxial film, pattern Hall bar, and then like to have a good proof, it's ideal to have some imaging, some tool to really image what is the magnetic state and how this magnetic state is eventually changing. And then how to do it. So magnetic force microscopy probably will not work. XMLDP I also didn't see working. There is a very nice report of this magneto-optical Kerr effect, but magneto-optical Kerr effect for our application has several strong disadvantages. One of them is that it's surface sensitive. We very much like to put something on top of our film, some capping, sometimes metallic. So all these interfaces are kind of causing some causing some interference, making like the MOOC a little bit uneasy. Moreover, it's spectrally dependent. So then comparing samples of different thickness or slightly different stoichiometry might be tricky. And also the geometry, this one was beautifully shown on the single crystal, where the rotation of the material is obviously easy. In our thin films, as I will show, we cannot select which direction points where. So there are certain restrictions which we kind of hope can be overcome by our technique, this scanning thermal gradient microscopy, which is sensitive also to the buried layers, and I will show that it can be also used to write the magnetic pattern to sample. So before I explain the technique, or Jörg already did a big part, I will just remind what is the anomalous Nernst effect, which is behind all this experiment, and what is the anisotropy in this particular material, mangan-3 tin. So anomalous Nernst effect in the easiest picture is just the thermal transport version of anomalous Hall effect. So voltage is detected or is induced perpendicular to a thermal gradient and some magnetic order parameter. And in this particular non-collinear antiferromagnet, in this mangan-3 tin, it has very prominent anisotropy. When the magnetic field is applied in A or B in plane, the signal is rather clear. When the magnetic field is applied along the C direction, then the signal is basically non-detectable. And then we kind of thought that this is a perfect candidate for our experiments, and we prepared together with our Dresden colleagues these thin films. And it turned out that the epitaxial, nice, high-quality thin films are growing very happily with the 011, with the c-axis to out-of-plane direction. So then one can immediately forget about this geometry, because when one would send the current in plane and have the magnetization to out of plane, then obviously we are in this scenario where we don't expect anything. However, this is actually very big advantage, as I will mention later, for the thermal gradient application, because the thermal gradient does not need to be applied only in plane, but can be applied also out of plane, and this is exactly what we exploited. So how is the main idea of the scanning thermal gradient microscopy? It's the same what Jörg was describing. The key idea is that there is a laser. The laser shines on a sample, and it creates a local thermal gradient. And this local thermal gradient is scanned on the sample, and then the global voltage, the induced voltage, is detected, which is then perpendicular to some magnetic order, and therefore it reflects the local magnetic order on the spot where the laser was shining. This is known in ferromagnets. In ferromagnets, obviously, it's easy. Magnetic field is reversing the magnetization, and then the detected voltage, the global detected voltage, is either positive or negative based on the magnetization. So, and how to use this in our non-collinear antiferromagnet? So we had our films with the c-axis out of plane. It's again this famous material with the Néel temperature around 420 K. And then we are scanning over the sample, and we are hoping to detect the contrast. And then what is the laser gradient, what is the laser induced gradient actually looking like? So obviously there will be some in-plane component. So the in-plane component in the middle of a perfect single domain material would be averaging out. However, there are also edges of the sample, as Jörg mentioned, and there are also these domain walls where the thermal gradient could be somehow making the in-plane component of the thermal gradient could play some role. But this is the lucky situation in the mangan-3 tin, that actually the in-plane gradient and the detection also in plane of the sample is not expected to give any signal. So this is what we also tested on the sort of large global scale, that we created such a lithographic device where we had heater which generated very strong in-plane thermal gradient. We detected the voltage also in plane, and then we applied strong magnetic field to the out-of-plane direction, and indeed one does not see any signal except of this ordinary contribution, some sort of ordinary Nernst effect. So this is the in-plane component. This does not need to cause us any headache. But then there is the out-of-plane, which we are actually interested in, and this is the favorable scenario for having the out-of-plane gradient, and then having this two, let's say, magnetic configuration. We call it Hall vector, somebody calls it octupole vector. Yeah, it doesn't matter, it's simply two different magnetically ordered grains or domains, and these two should yield different anomalous Nernst signal. So this is what we did. We prepared a Hall bar, such a Hall bar, and then in this we detect the voltage in these two contacts, and then in this small region we are scanning with our laser. And then what we are getting is indeed a colorful map with some red spots, blue spots, some spots with 0 voltage, and then we kind of hope, or we would like to see that these are really corresponding to different antiferromagnetic configurations. But to be sure or to prove this, we obviously need to show that it's of magnetic origin, that it's not just like some mountains and valleys on our sample, that it's not just a topography. So we kind of happily applied a magnetic field of half Tesla at room temperature, and we saw nothing. So we saw kind of that the pattern is unchanged, although the bulk mangan-3 tin in this configuration should be already reversed. We didn't see anything. On the other hand, we thought, okay, thin film, there is some strain from the substrate. It's always slightly different story when one has a thin film. So, excuse me. So, we were just repeating this scanning with the magnetic field plus minus half Tesla, and we could not see any difference. But we thought that let's not give up. It's a thin film, so the properties might be different. Let's try to go towards the null temperature and try to see if the lowering anisotropy helps. And indeed, when we were going to 400K and repeated exactly the same experiment, then we suddenly see like clearly blue, clearly yellow, which corresponds to the positive, negative voltage. Anomalous Nernst voltage. So we were really sort of convinced that our signal is of magnetic origin. Then we indeed also knew that the in-plane gradient and out-of-plane magnetic field also gives some response, which is linear, which is some sort of ordinary Nernst effect. So to exclude some sort of simple ordinary contribution, we also knew that we have to do the full hysteresis loop, which is what we did. We applied different magnetic fields ranging from minus half Tesla, going to 0 to plus half Tesla, and then going back, and measured the maps. So the maps are obviously varying, and when one carefully makes average of these points, of these carousel points, and plots it, then we are getting surprisingly nice hysteresis curve, which looks really like there is some saturation. There are some two states at 0. So this is not any ordinary signal. And what was also pleasant was that when we heated the sample even more above the null temperature, and we were again repeating the same tedious scanning, we really didn't see any signal anymore. So this was encouraging. We also did, actually a little bit later, experiment when we were not sweeping the magnetic field, but we were rotating the magnetic field. And then with the rotation, from our first naive expectation, we thought that we will just change the projection of this Hall vector, and that we will just see kind of colorful changing shades from yellow to blue. And to our little bit surprise or disappointment, we actually don't see that. We also see the same sort of breaking into some colorful islands, and then almost coming back to the same shade of blue, that there is not 50 different shades of yellow and blue, that it's really like breaking into some islands which are having more or less the constant. Once it's getting blue, let's say somewhere here, then it's keeping its value. So right now, this is also something where before we thought that it's some easy plane material, where we just kind of can more or less have the Hall vector following the magnetic field. This we are not so sure anymore. And I think that for all that, we will really need higher resolution, which is our current occupation, as I will mention on the beginning. So we also, I mentioned that there are some differences from the bulk material, that the anisotropy is obviously different. On the other hand, we were very nicely surprised that when we look at the Nernst response, the anomalous Nernst response as a function of temperature, we see these kind of characteristics, what we would expect, that it's obviously 0 above the null temperature. It's obviously decreasing when going to the low temperature. And when we compare our data with the bulk, with the data from ICLAS, we were ourselves surprised how similar the temperature evolution of the Nernst coefficient is for the thin film and the bulk. So although the anisotropy seems to be very much depending on, also we know, on small variation of stoichiometry of our mangan-3 thin films and everything, some of the features, some of the key features like the temperature dependence seems to be holding for both the thin films and the bulk. So then we also thought that we could maybe try to evaluate Nair's coefficient, try to give it a number. But this is one of these disadvantages of this technique, that we cannot measure the temperature above the film and below the film very easily. This is simply not so straightforward. So giving a number to the anomalous Nair's coefficient, it's not so easy as giving a number, let's say, some anomalous Hall conductivity or so on. But we thought, let's try. And we have to start with calibration of the thermal gradient. And so how we calibrate our thermal gradient induced by laser, we have to find film which is as similar as possible to our mangan-3 tin films, which is having the same lithography design, and ideally which is having very large anomalous Nair's effect. And for that purpose, we had our good friend cobalt-2 mangan gallium, which we just last year showed that it's a record ferromagnetic anomalous Nair's value for tin film. And we used this guy to evaluate the thermal gradient of our laser scanning thermal gradient microscopy setup. So first we had this sample patterned to the structure where we added extra heater and extra thermometers. And then we are really generating some thermal gradient. We are measuring temperature 1, temperature 2. We know exactly what is the dimension where we have the temperature drop, where we have the voltage drop. And from there, with reasonable precision, we can get value of the Nair's coefficient of 2 microvolt per Kelvin. And then we take this device to the scanning laser setup. We saturate it with the 2 opposite fields. Then we are getting the measured voltage. We know the anomalous Nair's coefficient. And from there, it's easy to estimate that our thermal gradient induced by the laser at this 10 milliwatt power was something like 2 Kelvin per micrometer. So then when we take this value, we use it to evaluate the Nair's coefficient of our mangan-3 thin film. Then we are getting something like 2 is the bottom guess of the anomalous Nair's coefficient. And when it's put to this beautiful legendary table, then it's obviously like, again, a record value. But we ourselves know that one has to be very careful. So first, it's a very local measurement. So we are measuring really very locally. This might be completely different than from all these other materials. We are measuring also the thermal gradient really. I think some of these data are, for example, measured with this PPMS TTO option. And if I understood correctly, then sometimes it's making the value much smaller or realistically smaller than what we measure with our on-chip heaters and thermometers. And then there is, of course, error definitely of our estimation. The spot size, the spot size is actually the most thing which I think that when we take the laser size, that it's kind of not giving that it's much larger, the thermal gradient, than only the laser spot size. So so this is how it is. And then I also mentioned that we are using this technique not only to image the magnetic patterns, but also to write. And for that, we are exploiting the nice coincidence that at room temperature, the anisotropy is very high, actually. On the other hand, at 400 Kelvin, the anisotropy is significantly lowered. And then what we are doing, we are using like the laser to lower the anisotropy, and then it's sort of heat-assisted writing. So we are first polarizing the full bar with half Tesla applied and high laser power. Then we select a certain region, which we are then scanning with this high power laser and magnetic field applied. Then the magnetic field is switched off, and with the slow laser power, we can then read such a pattern which was written. And this thing can be done there and back. It can be written then blue here, red here, blue in the middle. It feels like rather reproducible and easy. And once it's written, and once it's scanned only with the room temperature, then it seems to be inert to 6 Tesla field. So it's particular property of this sample, this material. It's of course not universally valid, but anyway, it's a nice feature of these samples. So as I mentioned, that we call it like domains, but it's a question if it's not more some kind of magnetic clusters what we are actually seeing due to our resolution. And this also means that the observation of the spin transfer torque might be simply uneasy with this particular method, because we are not looking at the one domain wall and one domain on the right, one domain on the left. So obviously, seeing something which is on the domain level motion, this might be not possible. The rotation data are suggesting it, and as I also mentioned, one advantage compared to MOOC is that the resolution can be relatively easily pushed down, and this is how we are making ourselves busy right now. First plan is that Jörg in Berlin will employ his SNOM approach, and the second is that we have colleagues who are having setup where the AFM tip is heated. In the same time, a magnetic field can be applied, and they are employing this setup just to rewrite exchange bias samples, and they are drawing like beautiful patterns with resolution 10 to 15 nanometers. So this is exactly what we are planning, or what we are doing right now, that we take our samples and we believe that it should be realistic to achieve much higher resolution with this technique, with the same principle but different experimental setup. So this brings me for now to the conclusion that we kind of showed it on this particular material, that its proof of principle imaging writing seems to be fine, and we are now trying to push the resolution down to really see maybe the individual domains. And also it seems that it's very versatile, that it can be applicable to many materials. It's not sensitive to some spectral properties or something like that. And this is also what makes us now busy. So yeah, these are again the colleagues, and thank you for your attention.